By the aid of the simulation, the responses of linear as well as nonlinear dynamic systems can be efficiently calculated using the same concepts. It can therefore be considered as the universal analysis approach in time domain. If the simulation goal is the calculation of model response to the chosen input signal, only one simulation run is executed. But sometimes the simulation goal can be the study how one or more parameters changes influence the model response. In such cases, a set of simulation runs is executed, and in each run, the studied parameter is changed. This approach is called also a parametrization. In the cases where the parameters changes are realized using selected algorithm with the goal to find the best possible solution of the problem, the term optimization is used. Let's present some useful solutions from the field of modeling and control system design. Let's observe the second-order system model as presented with the equation 2.1. Equivalent model presentation in the form of transfer function is illustrated with the equation 2.2, where parameters omega n and zeta have special names. Omega n is the so-called natural frequency, zeta is damping coefficient, and in addition omega d is the so-called damped frequency. Let's observe how changes in damping coefficient influence the system response if unity step input signal is applied to the system. We would like to observe four main situations. The first one is the one where zeta is greater than 1, and in such situation the system is defined as overdamped. We would like to plot corresponding responses in blue. When zeta is equal to 1, the system is critically damped. We would like to plot system response with the red line for this case. When zeta is less than 1 but greater than 0, the system is underdamped, and we would like to plot the corresponding output with cyan color. And finally, when zeta is equal to 0, the system is undamped, and the corresponding output will be presented with the green line. In all four mentioned situations, the natural frequency omega n will be set to 1. We have already built the corresponding simulation model in Simulink, which is saved under the name simmodel1.slx. Let's develop now an ASCII M file named myfile2.m for the realization of the described parametrization. The duration of all simulation runs will be 20 seconds. Here model parameters are presented. Omega n is 1 for all runs, while zeta is defined as a vector with 6 desired values. Next, we have to open an empty figure. Here its name, position, and color is defined. For loop is starting here, where 6 iterations will be executed regarding the observation of 6 values of parameter zeta. For each value, first parameters k1, k2, and k3 are calculated, and then simulation run is started. When the simulation run is finished, all signals connected to the workspace blocks are defined as vectors in MATLAB workspace and can therefore be plotted. We are going to generate two subplots in opened figure. The first one is presenting the input signal U in red, while in the second, the output signal is plotted in corresponding color. For zeta is greater than 1, the color is blue. When zeta is equal to 1, the chosen color is red. And for zeta is less than 1, in cyan. The final value of zeta is equal to 0, and the corresponding response will be presented with the green line. Let's start now my file 2.m and observe the consequences. Here the responses are presented as zeta is decreasing. Let's inspect once again all 6 settings of the parameter zeta. If the system is overdamped, no overshoot of the system response is expected. The system has in all such situations two different real poles. If zeta is equal to 1, the poles are still real, but are equal. The system response is faster, but with no overshoot. If zeta is less than 1, but greater than 0, system poles are complex, and system response has overshoot. Overshoot is greater if zeta is smaller. In the case of undamped system, the real part of both poles is 0, and oscillations are expected in the system response. Homework. Repeat the experiment parametrization for 3 different values of natural frequency for the underdamped system. Comment how different values of the natural frequency influence systems' properties. Here, a possible solution is illustrated. Parametrization as a simulation experiment can be very useful also in the closed-loop system operation. Let's illustrate one such situation as is presented with the block diagram in this figure. The model of the system is again defined with the differential equation 2.1 or equivalently with the transfer function given with the equation 2.2. This system operates in closed loop with a simple proportional controller with the gain Kp. We are going to change the value of the gain Kp from 0 to 20 and will observe how such changes influence system response. For this, a new simulation scheme, simmodel3.slx, was developed from the file simmodel2.slx. Here, only few changes were introduced. I have generated additional gain Kp and additional summator, where the first input to this block is the so-called reference signal and the second is the negative feedback from the system's output. Then we have to generate a new script M file, namely myfile3.m. Here the first part of this file is presented, where the duration of the simulation run and system parameters are defined. Next, the figure is opened, where the simulation results will be presented, and the first line of the while loop is defined. Here, in the third part, the value Kp is displayed first, and then the simulation run is started. Then, the first plotting functions present the reference and the output signal in the upper graph, where also the labels and the title are defined. In a similar way, also the control signal is plotted in the lower graph. The final results, when the parameter Kp is equal to 20, will be plotted with the red lines. Other responses will be presented with blue lines. At the beginning, when Kp is less than 2, Kp is increased in each step for the value 0.1, while later on for the value 1. Let's observe now how constructed file, when executed, calculates and presents the results. It is obvious that for the smaller values of Kp, the closed-loop system is overdamped, while later on the overshoots to the step input signals are increasing. This means that system has become underdamped. From this, it is possible also to conclude that when Kp is increasing, Also, the imaginary parts of closed-loop poles are increasing. Homework. Repeat the experiment parametrization and inspect also the pole positions of the closed-loop system. Test also the function RLocus and present the conclusions.